So everyone go.
Start. We will do the form again today.
Recording, share screen.
Nice.
Sorry, Dr.
Don't worry. So,
Please, when you're going to take the attendance, can you remove the line for connection to the?
I'm not sure if we're allowed to do that because of the safety. So, but I'll stay.
Because the connection here in the auditorium, I spoke to IT and they're saying they're trying to fix it. It's very slow. That's why.
Okay, I'll
most
remove
of
it.
the
I'll remove
students are not able to take it.
Awesome. Okay, I'll do it.
Okay, thank you, Dr.
No worries. All right, guys, I'm going to begin in a couple of minutes, okay? So just heads up. All right, okay, ladies and gentlemen, can we begin? Shall we begin? Right, okay, so nothing better than first thing in the morning and learning about spermatogenesis, eh? Awesome stuff. Right, okay, so if you remember on from my last lecture, we just covered the very principles of oogenesis. Now, today we're going to be covering the male component. And just towards the end, I'll be taking you through similarities and differences between the two processes, but also touch upon using a particular example on how errors can arise and lead to clinical situations or clinical complications. Now, before we begin, if you remember back to, yes? It's okay, that's because I didn't upload them. That would explain a few things, right? So I'll do it after the lecture, okay? What? Can I raise my voice? Microphone, can you raise my voice, please? So, I don't know, I think it's just one setting. I'll try to speak into it directly like this, yeah? I feel like I'm doing a concert. So, one of the key things you have to remember the basic terms that we went over, the basic processes, mitosis, meiosis, that sort of stuff, that is equally, if not a little bit more important for spermatogenesis. Now, where oogenesis was about maturation of the follicle in relation to the ovarian cycle, you also had a little bit of a stop-start mechanism as far as the oocyte was concerned. With spermatogenesis, of course, it is all hormonally based, but it's not, the hormonal cycle isn't as complex as in the female scenario. But what is much more complex are the intermediate cell divisions. So the type of cell divisions that happen throughout. So it's, again, it's not hard. It's just a lot of steps that you have to be aware of. And hopefully I'll be taking you through that and you'll be able to appreciate that a bit more. So in terms of talking about gametogenesis, we covered oogenesis the last time, and of course, this is in relation to the female reproductive tract. And the male component, spermatogenesis, or creation of sperm, is linked, of course, to the male reproductive anatomy. So again, going back right to the beginning, 10th week of development, similar starting point, the embryo is at the bipotential stage. It hasn't yet decided whether it's a boy or a girl. Stem cells will flow from the yolk sac. They will become PGCs by the time they arrive to the gonadal ridges. Yes? No, they're not even primordial germ cells yet. So they're stem cells and they're becoming PGCs while they're migrating to the gonadal ridges. So these gonadal ridges, these will, as we discussed, become the sex organs later on. So if the female fate is decided, then these gonads, of course, will become the ovaries. You will get the formation of the oviducts as well as the uterus and the vaginal opening as well. And the male components, which would have become the male components, would degrade. However, if there is a Y chromosome, remember, it's not more about expression, but rather inhibition of the female genes. The Y chromosome will inhibit the X chromosome component. And the gonads will start to become the testes, the epididymis, the vas deferens, as well as the seminal vesicles and prostate gland, and so on and so forth. So the male fate will result in development of male organs. Okay. So again, this is the key dividing point. Once this happens, once the gonads start to become the testes, this is where the PGCs will start to differentiate. This is where they will start to specify. Now, in the female scenario, this was differentiation into oogonia. In the male scenario, it would be spermatogonia. Fortunately, like I said, scientists lack imagination. So this is, again, the committed step, at least in vivo. Naturally, you will not be able to go back from spermatogonia to PGCs. The cell fate has been determined. So herein lies one of the first major differences between oogenesis and spermatogenesis. So as we talked about, the complex nature of oogenesis involved half of the process occurring before even birth, let alone puberty. The rest of this process then completed after birth and puberty. Spermatogenesis occurs only after birth and puberty. So what will happen at the embryonic stage, the PGCs will become spermatogonia, and that's the way they'll remain until puberty hits. Your spermatogonial cycle will begin in correlation to your first acne. But anyway. Now, of course, spermatogenesis, being the male component, is intricately linked to male reproductive anatomy. And you remember I kept on talking about the majority of a particular process being linked to a particular organ. And the same is true here for spermatogenesis. The vast majority of spermatogenesis will occur within the testes. But this is by far, by any means, not the only organ which is involved in spermatogenesis. Now remember, spermatogenesis here being defined as a process of creating a mature sperm capable of fertilization. Okay, so that's the key definition that you need to remember. But there are also other organs, like I mentioned, that are involved. Just above the epididymis, the testis, you have a structure called the epididymis. So after the sperm are made in the testes, they're transferred to the epididymis. They're stored here until they're required for ejaculation. After that, they then move into the vas deferens, and they will make their way through, mix up with, let's say, fluids to form semen. These are produced by both the prostate as well as predominantly the seminal vesicles. Now, the reason I'm going through this is all of these organs have a specific role in determining the health and rate and quality of spermatogenesis. So let's focus in a little bit. Let's start at the beginning. Of course, the majority of spermatogenesis will occur here within the testes. Okay. Just above the testes is this structure called the epididymis, and we'll talk about this epididymis as well. So the start will be here in the testes. Now, if you take testes and then make a slice through, what you'll essentially see is like a bowl of spaghetti. I love using this because you'll never be able to view Indomie the same way again. So it's miles and miles and miles of spaghetti-looking stuff. And these are known as seminiferous tubules. They're literally tubes, literally miles and miles per testis, all condensed onto each other. And if you take one of these tubes, you make a cross-section through it, essentially this is what it looks like. You have a wall outside, you have specific cells surrounding it, and then you have a hollow bit known as the lumen. Now, the key players here are these big cells called the Sertoli cells, slightly smaller cells outside called the Leydig cells, and of course, your Spermatogonia. Now, all of these are intricately linked, and these are linked to hormonal cycles at puberty. And yes, males also have cycles of hormones. So what will happen at puberty, you have all sorts of hormones all over the place, but specifically what will happen also in males, LH will stimulate, increasing levels of LH, will stimulate these Leydig cells outside, and these will start to produce testosterone. Now, this testosterone will act upon these spermatogonia, and this will kickstart the entire process. Okay? LH acts on Leydigs, Leydigs secrete testosterone, testosterone kickstarts everything here. Now, what will also happen, it's kind of happening already at basal levels, the Sertoli cells, they're kind of like the supermarket for the spermatogonia and for other cells within as well. They provide the nourishment, they provide the right environment, they provide all the good stuff for the cells to stay alive. But what will then happen, once the Leydig cells produce testosterone, the Sertoli cells will increase this production. They'll basically go into overdrive. And this is in preparation for spermatogenesis, because what will start to happen is tons and tons and tons of cell division. Yeah? So where females are concerned with quality, guys, we don't really care. Like, this number's fine. It's okay. So to accommodate this huge increase in numbers, you need a large amount of food. And this is what the Sertoli cells provide. They also provide and top up levels of testosterone. So the feedback between Sertoli cells and Leydig cells pretty much drives spermatogenesis. Now, you might be tempted to think that this is a continuous cycle, but it's not. Levels of testosterone, and despite what some of my male friends here will say, aren't always elevated. There are cycles of testosterone. There are waves. Goes up, comes back down, goes up, comes back down. So what will happen once this testosterone wave starts at puberty, these spermatogonia will start to develop into sperm cells. And they do so in the direction of the lumen. So if you start right at the membrane level here, and move towards the lumen, you'll start to see sperm in more mature states. So essentially, this is just the organization of the seminiferous tubules. Right, so this is where I'd like you to just bear with me, okay? Just go through the steps. Try to keep and categorize each step as we go along. Remember, it's not hard. If you think it's hard, take that out of your head. It's not, it's just loads of characterizations. So what will happen is when the spermatogonia are exposed to testosterone, at that stage, they're also known as type A spermatogonia. Okay? So within type A, there are two further types. So AD and AP. Now this D and P will make sense in just a little bit. What the D means is dark. So to begin with, the spermatogonia are type A dark. Once you have this testosterone wave, the spermatogonia will divide via mitosis. Okay, so we have no meiosis yet. This is still mitosis. And this will give you two daughter cells, right? So mitosis is a somatic cell. One mother cell gives you two diploid daughter cells. What's different in this process, though, is one cell will be exactly the same or more or less the same as the mother cell. The other cell, instead of being a dark, it'll be pale. It'll be lighter in color. And I'll show you a picture which will really demonstrate what this looks like. So what will happen is during the waves of testosterone, spermatogonia will divide. One population, which is more or less like the mother cell, will be used to replenish everything. So it keeps the stocks of spermatogonia constant. Herein is another difference between oogonia. Whereas in the female scenario, you have a limited amount. You have an oocyte reserve that women are born with. In theory anyway, in the male scenario, the spermatogonia never really run out because they're constantly replenishing. But what we're interested in at this stage is this, the pale spermatogonia. So after mitosis, a dark has led to a single pale. What will then happen is this type A pale will start to differentiate, it'll start to specialize. And it goes from a type A pale to type B spermatogonia. So it's that straightforward, it's just different names, not very imaginative names at that, okay? So you have to remember at this stage, they're still diploid cells. They have not yet even entered meiosis, but differentiation has already started. Now, to illustrate further to you what we mean by pale and dark, during reproductive biology, as most histology and cytology is concerned, really the only tool you have is a microscope, okay? So most of your characterizations is going to be based on a beauty contest, on how things look. And of course, when we're doing analyses of this is no different. We're doing a little bit of staining. Predominantly, when we do staining for tissue, we're staining the nucleus, right? So the pale and dark characterization comes from how darkly the nucleus is stained. So this is a picture, testis cross-section, seminiferous tubule. And what you can see is that some nuclei are much darker compared to others. Yeah, so this one is darker, and these ones are pale. So this is based just on the intensity and the size of the nucleus. These are type A dark spermatogonia. These are type A pale. Now, essentially what's happening during this differentiation process and mitosis process, what's happening is that the DNA in the type A dark spermatogonia are really, really condensed. It really kind of scrunched up onto itself. But when it becomes a type A pale, the DNA is now starting to become looser. Okay, much more spread out. So the staining intensity isn't that it's not that intense essentially. So it's a much lighter color. Now this is important because this is a key indicator that the process has started. Because the DNA is becoming much less associated with itself, it's getting prepared, it's being modified to undergo meiosis. It's also being modified for numerous other processes that we'll cover in just a little bit. So what will then happen as you proceed through spermatogenesis? Type B spermatogonium will become a primary spermatocyte. Now the differentiation is really beginning to pick up. And again, it's very easy to see in a histology image. The spermatogonia generally are much darker. The nuclei are much, much more condensed, hence why they're much darker. And the primary spermatocytes, the DNA is yet even more loosely associated, even more so than the type B and type A pale. So again, it's differentiating further. All at this, up until this stage, mitosis. Now, at this stage, and in relation to levels of testosterone, primary spermatocytes, which are still diploid, these are the ones which will enter meiosis, the first round of meiosis specifically. So one diploid primary spermatocyte will give you 2 secondary spermatocytes, which aren't completely haploid yet, but they've entered meiosis. Then what will happen is that these secondary spermatocytes will enter meiosis too. These will give rise to fully haploid spermatids. Okay? So key things to remember: spermatogonium will become primary spermatocytes. This entire process is purely mitosis. The spermatogonium are of 2 different types, the type A and type B. The type A are of a further 2 different types, dark and pale. Okay? So again, not hard, there's lots of terminologies. The meiosis will start at the primary spermatocyte stage, give you secondary spermatocytes. The secondaries will enter the second meiosis, and these will give you the haploid spermatids. This is just a summary to put everything together the way it's going. So here you have your surface of this tube, the seminiferous tubule. You have your spermatogonia, the Sertoli cells are surrounding it as well. And what's happening in the direction of the lumen, you're getting your type A dark, type A pale, type B, primary spermatocytes, and secondary spermatocytes. Right at the end over here, you will have your spermatids. So within this membranous, this wall of this seminiferous tubule, you will have everything from spermatogonia all the way up to spermatids. Okay? And they're more or less now what you would expect a sperm cell to look like. However, we're still not done. The sperm, pretty much, they still do not look like this picture that we're used to seeing. You could actually say that at this stage, only half the process is done in terms of manufacturing this cell. So what will happen? You'll have mitosis and meiosis. You'll have cell divisions up until the spermatid stage. And this entire process is still spermatogenesis. But what will happen, the spermatids, instead of going through further cell division, so cell divisions are now going to stop, these spermatids will enter a specific process within spermatogenesis called spermiogenesis. Okay? So important to remember this. Spermiogenesis is a part of spermatogenesis, but it's a unique and specific part. So what's happening here is that these spermatids, these rounded cells, are being literally physically transformed into spermatozoa, sperm, the mature cell. And essentially, it's a reorganization process. And it's wonderful. It really illustrates just how nature is the first recycler. All of the components of the cell which aren't needed aren't discarded, but reutilized and reorganized. So what do you think you need? Let's say you're a sperm cell, yeah? Put yourself in the tiny shoes a sperm has to put itself in. What are the things which are necessary for you to get you to an egg? Tail, what else? Sorry, speak up. Energy, what else? Yeah. Acrosome, why? Good. So what you need to do, absolutely correct, well done. What you need is the ability to get to the oocyte. You need the energy to be able to do that. And you remember those big structures that we talked about? The zona pellucida, the cumulus cells that are surrounding the oocyte? You need to get past those. But at the spermatid stage, the sperm doesn't have any of these. It doesn't have a means of propulsion. It doesn't have a dedicated energy source. It doesn't have specific methods to get past these particular barriers on the oocyte. So spermiogenesis is the acquisition of all of these, more or less. Not in its entirety, but at least it begins acquiring these. So what will happen is at the point of spermiogenesis starting, the cell will reorganize itself. So you know the cytoskeleton, the components, the architecture of the cell, that'll begin to be reorganized. So what will happen is that the entire cytoskeleton, the actin, the tubulin, everything will start to align at the base of the nucleus, at one base rather. Now, how would you know which is up and which is down? Well, that is determined by the formation of another specific vesicle. So most of the organelles, the membranous organelles, in this particular case, the Golgi apparatus, including the endoplasmic reticulum, the lysosomes, and the peroxisomes, they will start to break down. They will start to degenerate in some ways. But what will happen is that the majority of the Golgi apparatus, in conjunction with all of these other breaking down organelles, they will start to form this cap-like structure at the end. Now, the pole at which this cap-like structure forms, the opposite end of it, that's where the microtubules will start to align. Specifically the centrioles. It will start to basically form this axis. Now, this cap of Golgi apparatus, eventually it will engulf the top of the head. It'll form this, it's kind of like a hat, a cap at the top of the sperm. And this will become the acrosomal vesicle. Now, this acrosomal vesicle, because it's incorporated stuff like lysosomes and peroxisomes and the Golgi apparatus, it's going to contain lots and lots of enzymes. And these enzymes are important for fertilization. We'll talk about that in the next lecture. But what will then also start to happen while the acrosome is forming, the cytoskeleton is aligning, specifically the microtubules. And these are being reorganized to form the tail, also known as the flagellum. Now, don't be mistaken in thinking that it's like a single tube. Actually, no, it's not. The most accurate way to describe a sperm tail is, take a few ropes or some string and kind of twist them around each other. The type of structure that forms, that's what the tail looks like. So it's all of these cytoskeletal elements, the tubules, the actin, they're wrapping around each other until they form this flagellum. Now, everything else, the cytoplasm, the cell wall, this huge amount of intracellular space, what do you think it's going to do to the sperm if it's still attached? It's going to slow it down. It's all this excess stuff that you don't need. Do you need ribosomes in a sperm? Do you need endoplasmic reticulum in the sperm? You don't need much in the sperm. Really what you need is a few proteins, relatively speaking, and you need the DNA. But one important organelle that you do need, what is this going to be? Mitochondria. All the mitochondria of the cell are aligned at this pole. And this will form a structure called the midpiece. And this is the battery of the sperm cell. This will provide the energy requirements the sperm needs. All the other stuff, the cytoplasm, the remainder cell wall, yeah, it's kind of like undergoing this pinching off like action. So it's depositing all the protein, all the organelles, all the mitochondria that it's needed along this forming flagella. But eventually, it's going to be the excess cytoplasm is going to be discarded because you quite simply don't need it. Yes? Sorry? So it's the formation of the acrosome that determines the top part, and then the tail part will automatically form under the just directly underneath it. That forms the pole. Okay? So once spermiogenesis is complete, then you will start to see this structure that we're all used to seeing. You have a head covered by this acrosomal cap. You have a midpiece, which is rich in mitochondria. And you also have a tail, which is predominantly composed of microtubules. So again, as another summary, just to put it into perspective for you, you have the majority of spermatogenesis will occur within the testis, specifically within the mild and mild spaghetti seminiferous tubule-like structures. Yeah, I'm saying the spaghetti on purpose. I want to gross you guys out. So within these seminiferous tubules, you have two components. You have the wall part and the lumen part. The spermatogonia at one end of the tubule, and the mature sperm within the lumen. So specifically here, you have your mitotic divisions, your meiosis divisions, then you have spermiogenesis, and this will give you the mature sperm. Well, mature, quote unquote. Now, a single cycle of this from start to finish takes around a couple of months, okay? In most mammals. In humans, it's a little bit less, but more or less, humans fit into the mammalian category. But you see, it's not one cycle happening at any one time. So remember, levels of testosterone aren't always elevated. I talked about waves. So each wave of elevation will result in a cycle of spermatogenesis starting. Okay? So once after puberty, once the waves are initiated, it is a very, very rapid process. Tons and tons and tons, literally, of these cells are made on average every single day. On average, once the cycle is started, one testis, will be producing around about 300 million sperm per day once this cycle is undergoing. So this again is to serve as a summary for you. It's put into context at what stage mitosis is happening and what stage meiosis is happening and what stage the spermiogenesis is happening. But the key thing is that this specialized structure that we talked about, that's made at the end of spermiogenesis. So the end of spermiogenesis corresponds to the end of the largest part of spermatogenesis. However, we're still not done yet. Because even though they look like sperm, they're not capable of fertilization. The biggest issue is that these guys can't swim. They do not have the ability to swim. They also don't have the ability to recognize the oocytes. So if you were to take in vivo sperm which have just finished spermatogenesis, this would be infertile sperm. What they need to do is undergo specific modifications. And this is where the epididymis kicks in. Remember, you have your testis, and on top you have the epididymis. So once spermiogenesis is finished, by that point, the sperm have reached the junction, or they're transported to the junction. Now, the junction between the epididymis and the testis is known as the rete testis, R-E-T-E. Some people might pronounce it the rete testis. Now, at this stage, they're transferred to the epididymis. And the epididymis is a type of these tubule-like structures. So it's not Indomie, it's Maggie, basically. So, sorry, it's getting a bit tired. But essentially, what's specialized about these tubules, instead of having different types of cells, you have a big, thick epithelium, specific epithelial cells. And what these serve they serve as kind of like these parking spaces, these docks for the sperm. Quite literally, the sperm will shove themselves into these parking spots over here. So you see this? These are the tails, and these are the sperm nuclei. So the sperm will come in and they will park themselves into the epididymis. And this will happen throughout the length of this. Now, the purpose of this docking is that the epididymis, while the sperm is docked, and while the sperm actually is also being transferred along the epididymis, it will be modifying the sperm head and the sperm tail. So one of the things that's happening are surface modifications. As the sperm is moving through the epididymis, tons and tons of protein are being deposited on the head of the sperm. At the same time, the head is also being remodeled. Yeah? So it's like a jigsaw puzzle, pieces are being moved around, but at the same time, tons and tons of protein are coating the sperm head. After the epididymis, when it's time for ejaculation, the sperm will be mixed in with a specific liquid called semen. Now, this semen contains lots of other stuff. We'll cover that in just a bit. But being inside the semen coats the sperm even further. It adds even more coatings. Now, the purpose of this kind of capping, this coating, serves as a protection. Okay, you have a huge amount of distance the sperm needs to cover, even before it enters the female reproductive tract. You want to protect this cargo, this DNA and protein that needs to be delivered. And from the perspective of a sperm cell, ejaculation is a very violent process. So you need protection from that. The pH also changes. So when you go from leaving the testis to in the epididymis, this huge change in pH will cause this excess cytoplasm to break off. Kind of like becomes a little bit more acidic and the cell just kind of nips off. But this change in pH also modifies the tail. And as it enters the seminal plasma, the tail is modified even further. So really, the sperm acquire the ability to swim after they leave the testis. In fact, they complete this acquisition not within even the male reproductive tract. It's once they're being ejaculated, that's when they acquire fully the ability to even swim. And a large part of this is because of semen. Now, the vast majority of semen is produced by the seminal vesicles, but you also have large contributions from what's known as the prostate. Now, to cut a very, very long story short, both of these organs, or glands, if you might, are producing different types of secretions. This will collectively serve to give you semen. Now, inside, you've got lots and lots of stuff. You have stuff like citric acid and enzymes. But you also have, from the seminal vesicles, you will have nutrition. So vitamin C, fructose, the energy source. And this serves to not only recharge the sperm while they're inside the semen, but also to make sure that the nourishment is met so that the sperm are being kept alive until they reach the urethral opening. This is inside the female reproductive tract now. But you see, almost counterintuitively, this process of protecting the sperm adds yet another barrier. So think of it this way. You have a sperm. To protect it, you've coated it with so many different things. But because you've coated it with so many different things, how is it now going to bind with the oocyte? How is it going to recognize the oocyte? So it's kind of like shooting yourself in the foot, but it's a very elegant protection mechanism. So what needs to happen is all of these modifications that you've done to protect the sperm, you now need to remove them. And the way in which this is done is via a process called capacitation. Okay? So this is just, it's lots of biochemical signaling. You don't need to know what the signaling is about. I'll go into a little bit of detail in the next lecture, but apart from that, all you need to know is that capacitation involves further modification of the sperm heads. So one thing that capacitation will do is that it will remove all of these proteins that were coated onto the sperm head. Now, what's really, really cool is that when the sperm is inside the semen contains what's known as decapacitation factors. So it prevents this process from actually happening. So it prevents the sperm from reaching full maturity. But once the semen is inside the female tract, it becomes diluted. So the action of these is diluted as well, and then capacitation is allowed to happen. So the final process only is allowed to happen once the sperm has left the male organs and entered the female component. It's a really, really elegant way of ensuring that processes happen when they're required to happen. But you see, because it's a biochemical process, it requires all sorts of energy, it requires all sorts of further modifications as well. So not only are you removing the surface coating of the protein, you're literally modifying the sperm head itself. So imagine if the sperm membrane looks like this. After capacitation, quite literally, the membrane will turn inside out. Now, what's really cool about this is that when the membrane is like this, you have receptors, specific receptors that are required to recognize the oocyte. Before capacitation, they're facing inside towards the nucleus of the sperm. After capacitation, become like this. So after capacitation, the protection of the sperm is removed, and that's when the sperm are now finally able to even recognize the oocyte. Yes? Sorry? That is a specific issue in reproductive sciences, but the sperm actually doesn't even, and predominantly doesn't even come across immune reactions. The majority of immunity is against semen. And you'll notice this in the next lecture as well. There's specific strategies to ensure that these sperm cells are protected within the female tract. Now, this isn't the only process that needs to happen. So you've had capacitation, it's a biochemical series of processes. But once capacitation is happening, another process will happen, almost as a product of capacitation. This is known as hyperactivation. Okay. Now, in popular science, when you've heard people talking about fertilization, often you might have heard it being described as a race, at least within the sperm. And in many ways, yeah, you know, healthy sperm means quicker swimming sperm. Quicker swimming sperm will mean that the nucleus is better, the quality of the sperm is better. So speed is a good indicator. But it's not just as a selection mechanism. The speed or the rigorousness of the motility of the sperm, that's also important physiologically. So remember, the oocyte is coated by multiple barriers. The first of these are the cumulus cells. So the sperm, they need to force their way through it, as well as the zona pellucida. Now, if your tail is just like this, you're not really going to be able to do anything. So what hyperactivation does is that it causes this vigorous beating of the tail. So the sperm moves not just with more speed, but with much more force. So both of these processes, capacitation and hyperactivation, are an absolute requirement, at least in vivo, for the completion of fertilization. So really, if you want to define, again, similar to oogenesis, if you really want to define the production, spermatogenesis, the production of a mature sperm cell that is capable of fertilization, then yes, the process starts and the predominant part of it occurs within the testis. But really, mature spermatogenesis, if you take into account capacitation and hyperactivation, Spermatogenesis really completes in the female reproductive tract. So it's this really series of unique series of very elegant mechanisms that they're the kind of these checkpoints. Like, have you completed this? Okay, let's go on to the next stage. Have you completed this? Let's go on to the next stage. The reason for this is that sexual reproduction requires a lot of energy at all levels. And you don't, to survive as an organism, you don't want to just expend this energy unnecessarily. So these series of checkpoints really ensure that proper fertilization, proper embryogenesis will occur. Now, the gametes haven't even met yet. They haven't even started to make their way to each other yet. And they have so many things that they need to go through. So just as a summary, this is a really cool slide, I think, because it compares both spermatogenesis and oogenesis together. Again, they're very similar processes, but unique in their own right. You really need to know the context of these cell divisions in the context of mitosis and meiosis. But of course, there are unique differences, some key differences, which you really, really need to appreciate. The first of these is that spermatogenesis is a continuous process once it starts. With oogenesis, you have multiple starts and stops. So you have one round before birth, it stops. Puberty, you have another round, but it stops just before ovulation. And then it's completed after fertilization. Now, another major difference is, as we mentioned, Spermatogonia will be replenishing because of the mitosis events that are happening. The type A dark will constantly be replenishing itself. Oogonia are limited in number. Okay, there's no replenishment activity that's going on. Another key difference, because of the way in which the cell divides, in oogenesis, one mother cell will give rise to one daughter oocyte. In spermatogenesis, because it's more straightforward cell division, one mother cell will give you 4 haploid sperm cells. Okay? And another summary, but the reason why I'm putting this summary on to you is that coming back to the original starts of our lecture series, we talked about mitosis and meiosis. And really why it's important to understand the difference between the two in terms of how DNA is distributed. Okay? Now, this is important because some of the things that are happening, well, at least for gametes, proper genetic distribution is required, it's absolutely essential. The reason for that, the reason why your gametes need to be haploid is that they will combine with the other gametes and form a diploid individual. If this genetic component is not distributed properly, this will result in fatal and, more worryingly, non-fatal but drastic genetic diseases. Now, apart from the genetic diseases that could arise, and I'll touch upon these in just a bit, these processes, as we mentioned, there's so many different checkpoints, there's so many things which could influence the quality. Because of that, you will start to get abnormal gametes. In terms of morphology, shape, remember, the biggest tool we have at our disposal is a microscope, so the biggest characterization of abnormalities is based on the shape. Now, in terms of the sperm, this is where the vast majority of abnormalities will lie. Just because you have one testis producing around about 300 million cells a day. Just by statistically speaking, you know, even if 1% of these are abnormal, just translate it. A day, you will get tons and tons of abnormal cells. And these will range in a huge variety. So if this is what a normal looks like in the lateral view, you can have giant heads, you can have tiny heads, you can have double heads, you can have double tails, you can have this weird spaceship looking stuff, as well as this weird noodle-like looking stuff. And so these are just an example, an illustrative example of how abnormal sperm cells can be. But here's a really funny thing. Any given normal male ejaculate should contain a certain percentage of these abnormal cells. Yes? Sorry, speak up. So, depends. Most of the time, such abnormal sperm won't even be able to fertilize. But if it does fertilize, most of the time such sperm won't be able to lead to an embryo. But if it does lead to an embryo, then it very much depends on further. So is the genetics fine of that cell? Are the further components required for embryogenesis, the sperm mill, are they normal? Okay, so the chances of even guessing a baby is very, very low to begin with. You add all of this, it becomes even lower. So the answer to that is not necessarily. But not only in the sperm, you also get more abnormalities within the oocytes as well. So you can get follicular abnormalities, such as this over here. In a single follicle, you have multiple primary oocytes which begin to mature. Now, this isn't a problem per se. They should still be normal, but what will start to happen within that same follicle, these cells will start to compete for resources. And eventually what will happen is that they'll start to cannibalize each other and they won't be able to reach maturity. You can get differences in size. This is a normal oocyte. It's a teeny tiny one. This will not have the capability of fertilization. We can also get these cytoplasmic abnormalities. So you see how it doesn't really look normal. It's not really touching the edge of the pre-bit line space. This is because probably the membrane is somehow abnormal. And this, even though it might be able to fertilize, probably the developmental capacity isn't spot on. But some of the major things that you will need to be concerned about, at least which is forward in terms of drastic consequences, is that of genetic abnormalities, specifically something called non-disjunction abnormalities. Now, where this comes from is essentially the chromosomes aren't aligned properly and thus aren't distributed properly in the daughter gametes. So what will happen up until this stage, everything is fine. You have, after DNA replication, you have 46 sets of chromosomes and an X and a Y. Now, in the first mitotic division, because the chromosomes aren't able to align properly, they will not be distributed properly. So what you will get is one cell with 24 chromosomes instead of 23, with an additional sex chromosome. Whereas the other one will have one less chromosome. So instead of this one being either only X or only Y, it's become an XY. And this one has no gender. So this gametes will then continue, of course, to complete the second round of meiosis. But this sperm is going to be useless. If this manages to fertilize an oocyte, then the oocyte will not form an embryo because it only has one sex chromosome. What's more, so this would be a fatal error. Embryogenesis will not proceed. In this case, however, you have a gamete, the sperm cells will be XY. Now, if these fertilize an oocyte, the genetic component will be XXY. Now, this is not a fatal event. You will get an embryo, but you will start to get genetic diseases. For example, Klinefelter syndrome. And a similar process can also happen within oocytes, where when the first polar body is extruding, this DNA distribution is not done properly. So this will be XX. And if you have a sperm that's coming in, you will either have XXX or XXY. Again, genetic conditions arise. So that's it for the gametogenesis part, okay? What we'll do next time is go through quickly how both of these gametes come together to produce fertilization. So we're talking about the first week of development. Thank you very much, everyone. I'll just quickly put on the I don't think so. I don't think so. I don't know. I haven't been approached for questions here. Richard, can you just give me a minute just to put this on hard? Do you know how to? So, do you know how to remove the internet restriction thing?
It's supposed to be at the top. And this is changing.
It's a different session. Let me just go back. So there we go. We'll go back. Okay.
1 second. Just load.
Okay, so all right. Okay, 60 seconds, fine. Wonderful, thank you.
Doctor, I just have one question.
Sure.
What can cause the genetic disorders that you just talked about? The information, XXY. Does it have some?
Load of different things. It's not one particular process. Abnormal cell divisions, stressful cell division conditions. So, I don't know, stress, for example, abnormal diets, abnormalities in the products that you take, so environmental toxins, shampoo and body soaps that you use. No, I'm not joking. I'm not joking.
Yeah.
That
was a weird one.
So for secondary spermatocytes, they go through meiosis 2 after, right? So like they themselves have finished meiosis 1.
So the primaries will enter meiosis 1, finish meiosis 1,
And then
and they're
give the
second.
So
The
shouldn't
secondary will enter the second.
shouldn't they be diploids then because they haven't finished meiosis 2?
No, they're not diploid because the DNA is now being separated,
Okay.
but they're not complete. So before the cell division is completed, they enter the meiosis again, and then so the two dorsal cells, while they're dividing, they're not divided yet. They begin to divide into further two.
So would they be haploid then?